start saying a few things about my course. Many of you might be wondering why this IIT faculty do not produce slides and give nice slide presentations. Well, fundamentally I am against making slide presentations, and that is because first of all it takes a lot of effort to make those slides, and the second thing is that it somehow makes it less interactive. Sometimes I want to say things in a particular order, I want to put out things in a particular order, and once you put on that whole slide, they have read everything already. So, if you do not want to do that, then play your cards close to your chest, as they say, and just let out one line at a time. So, I go by the blackboard. Even to teach this subject called signal systems and circuits, we use the blackboard. Now, as you all probably know, the subject of signal systems comes historically a little later. Again, it is a little bit of history, but not too much. A little after the whole business of electric circuits was around for a while. For a long time, even when I was a student in the 1980s, we were really not taught this whole theory of signals and systems as a separate course. It was just a little add-on to a course on circuits, advanced circuits, Van Valkenburg, etc., etc. You remember those books, I guess it is still being used. But the point was that much of the knowledge at that time was concerned with making circuits do certain things, but that was because of the state of technology at that time. When if you wanted to get something done, you first looked into what is the circuit which can do it, and therefore, people examined questions like should we use this kind of a network or that kind of a network. I remember one absolutely horrendous course following a book by, I do not remember, networks, lines and fields or something.
Yes, Potter.
No, it was not Potter, some Rider or
Rider, Potter.
Something, yeah.
Rider.
And we had all these things about two-port networks cascading each other, characteristic impedance, this, that. Let me tell you that I do not remember any of it now. I did not even remember at that time, but it was horrendous. And the reason, a large part of it was required to be learned at that time, is we did not have circuit blocks which behaved nicely in terms of having a high input impedance and a low output impedance. The moment that became available, you really could get rid of the theory, and effectively it has happened. We do not really, once you have something like an op amp, even though it is not really perfect, you can do lots of things far more simply. So, that is the idea behind simplifying and minimizing the circuit theory content in this course, in these courses. Eventually, in IIT Kanpur at least, the circuit part of the course keeps shrinking day by day, and the signal systems part keeps growing day by day. One day it will eat it completely, and I do not know when we will be teaching electric circuits or at all the conventional circuit theory. That is what I mean to refer to. So, right now we do have a certain amount of electric circuits and networks, which is taught in the same course, either in the beginning or in the end, depending upon how I feel like doing it, in addition to signal and system theory. So, I just want to outline this. In this part, I emphasize largely on the purely theoretical concerns involving electric circuits. The fact that electric circuit theory, for example, is confined to certain operating conditions of low frequencies, small circuit element sizes and so on. So, that we do not start bringing in line effects and stuff like that. And whether or not it makes sense to the student, I do say it up front and say that this is how we approach this material. Once that proviso has been put, we do a conventional study, we go from solving DC circuits with resistors to gradually talking about more complicated kind of characteristics like nonlinearities and elements which are controlled by voltage, but not by current, current but not voltage, or even by neither sometimes. So, that we get a grasp of what things actually happen out there and what things the theory is talking about. Sometimes the theory makes claims that cannot be verified in practice. Sometimes there are practical things you can do which the theory cannot explain, and both these need to be put before the student to say that here is the real world out here which behaves in certain ways, and here is the theory that has been allowed, that has been built up to handle it, which has its own concerns. We invent notions and ideas in electrical engineering, as we all know, which are not even considered quantities by physicists. We have built them and we are happy to live with them. And so, that is the same thing over here. We have our own ways of handling things. For example, circuit theory simply cannot tell you what will happen if you put two charged capacitors with different levels of charge, that means to say with different voltages, in parallel with each other. Just connect them to each other, what will happen? It just can't tell you what will happen. Though of course, nobody can stop you from doing that experiment in the laboratory and seeing whatever happens, but the theory can't tell you what will happen. So, the theory comes with its own paradoxes, with its own limitations, and then there is the real world out here. This kind of a dichotomy persists as long as we stay in the very fundamental entry level point of circuit theory, after which we deal with some network analysis. Basically, how to solve networks. So, there are lots of theorems and we teach all those theorems, and then there are all these techniques, methods of solving them by reduction and by nodal analysis and mesh analysis and loop analysis and all this. So, we go through all this stuff. By this point, we have really pushed the real world of circuits out of their heads and replaced it with our artificial world of circuit theory. And so, there are less controversies to be faced in the classroom. People have already said, yeah, what is happening in the blackboard is the real thing about circuits, do not worry about what happens outside. If something else happens, then we can go and look into what is the problem. So, this takes about 30 to 40% of the course. That is about maximum 15 lectures, a minimum of around 10 or 12 lectures. This is what we cover in the first part of the class. I will try to wind up very quickly, because I want to have discussions about this. I know lots of you will sometime or the other teach this subject. By the way, I have also put up an NPTEL version of this. This does not cover any circuits, this is just signals and systems, which is what I would really love to have even in this place, if I could afford it, to teach only signals and systems for a whole course and also teach circuits for a whole entire separate course, but that time cannot be afforded in the program. So, it is never going to happen. So, when we come to signals and systems, I would like to divide the content of signals and systems in the entry level course into signals and systems into what I would call communication and control. Okay. Now, we really do not touch much of the last part in the basic course itself, but we do go through the first three parts in some amount of detail. So, the first part, you would be surprised, probably not among the IIT students, but a lot of students that I have taught in the past do find it very difficult even to properly, I mean they have not even properly grasped the notion of a function. So, these things have to be introduced properly. It does not matter if it appears that you are beating a dead horse, but it is still very, very important to get the basics right, and that is why for me this is probably the most significant part in the entire course. You have to teach them properly about this and the properties to make them exactly understand what we are saying at every. And in this, the definitions matter a lot, but the examples also matter quite a lot. Creating a lot of examples and counter examples at every stage and showing students that this is an example of this property, like stability for example, I am sorry, and this is not an example or an example of not having this property, and so on. There are also relations between properties. For example, memory and causality are related in some sense to each other. So, these are notions that we should bring out clearly and say, if a system is causal, it may or may not have memory, but if it has memory, it is still causal. I mean, if it is memoryless, it is still causal. Things like that, there are many things to be said in that connection. And examples and examples. I will just give you the really nice cunning examples. Differentiator. So, you see y t now, first of all, people with a more classical approach towards signal system theory will say this is not even a system. This does not qualify to be called a system in the conventional sense, where a system is defined in the old way, but here we are just looking at it as anything that satisfies this box model, and so a differentiator is also a system. So, suppose we ask the question, does a differentiator have memory or not? Yes. It has memory. Now, can we prove it?
In the discrete domain we can prove.
No, I want it in the continuous domain. So, in the continuous domain, does it have memory or not? So, this is a very, very interesting question, and nobody is really talking about this really. I have not seen any of the books at least talking about how to settle this question once for all. So, I will bring this up later if I have time. So, these are all things that I believe it is worth investing time in when we teach this course. I would go through this part of the course nice and easy, nice and slow, let them take it in, there is no big deal there, it is worth it. Now, under interconnection, what happens if you interconnect two systems without memory? Can it become a system with memory? Probably can't. What about two systems with memory? Can it become a system without memory? Interesting to think about. This is endlessly fascinating. In fact, at one time my PhD was largely on questions like these, very, very entry level questions, can be very, very engaging. Now, after this, there is a considerable amount of ground to be covered in the transform domain, and here I used to teach the discrete part separately, then the continuous part separately, then things like the transform domain analysis for periodic signals separately, non-periodic signals separately, and all that. But I believe that is a cumbersome way of doing it. Over the years, I have kind of evolved to teach them all in sort of parallel. In this lecture you talk some of this thing, bring it to some level, then bring up the continuous case, bring it to some level, then go back to the periodic case, then go back to the continuous, go back to the non-periodic case and so on. Oops. So, if you do all these things in parallel, and before that, even before we go to the transform domain, there is this impulse function. Maybe we should say a few things about the impulse function and or impulse as we call it, not the impulse function, and what is the safe way to introduce it to students. Of course, there is something the book says and you can blindly copy what it says, but if you have already spent time telling students about what is an impulse, then you can't just throw it on their heads and say this is an impulse. That way of teaching it is itself an impulse. So, you should, I like to at least introduce an impulse as a limit of a sequence of functions, each of which is itself legitimate. So, it is sometimes very challenging when somebody says does an impulse have this property, does it have that property, and I would never want to touch it directly, it is one of those hot potatoes. So, I will go back and say, and by the way it is not the limit of a particular sequence of functions, there are several sequences of very ordinary functions that can be, that end up being the impulse. You just have to keep, you have to have a function which has some non-zero support and some positive area, and you keep shrinking it and maintaining the area, and it becomes an impulse eventually. So, what I do is, if you have any question about the impulse, does an impulse do this, does an impulse do that, do not face that question. Go back to the sequence of functions, to any one of the sequence, it could be the rectangular pulses, it could be the triangular pulses, it could be these. Or it could be any of these families of functions, and see if this property that you are looking for is maintained by every member of the sequence, equally maintained by every member of the sequence as you go down the sequence. And if it goes well all the way, then I am sure you can say that yes, the impulse will also have this function. If on the other hand it does not go all the way, if things start blowing up as you go down the sequence, then you can be sure that that property will not be upheld. But this is a very general statement, I guess it has to be qualified on a case by case basis. So, this is about the impulse, I wanted to make a point. And then going back to the transform domain, as I said, I try to teach it all in parallel, so that people can see the similarities between all these Fourier approaches, that basically you have a set of basis functions of different kinds for different kinds of representations, and that you have a transform where you represent signals in terms of those basis functions, and then you reconstruct the signal from those basis functions using the the spectrum. So, this I find is better achieved by taking a more compact parallel approach. So, this part is very dense and it is covered in at most say 7 or 8 lectures, and it finishes everything. Then in the last part, where we of course, we cover the Laplace transform as well, and if time permits the Z transform, where we emphasize what we are about to do here, what information we are about to gather here, which was not covered in the Fourier analysis. Then finally, this sampling reconstruction is one thing we cover, and the dependent courses succeeding this in our curriculum at least, like communication, introduction to communication, the principles of communication, introduction to control, all these things take up the other applications. But sampling I think is critical. We have to talk about sampling, because all through the course we have been talking on one side that there are discrete systems and discrete signals, and then continuous systems and continuous signals. And students really can't see how to cross from one world to the other if they want to, and that crossing part is very important. Very often when we teach them about this part on sampling, they still do not make the connection between what is this highest. Suppose I have some practical system with say 1 kilohertz or maximum bandwidth of 1 kilohertz, and you do sampling and then you convert it into a discrete time signal and you take a DTFT or something, then those frequencies are from minus pi to pi or 0 to 2 pi, and here you have everything from whatever to whatever. It can be from 1 kilohertz to minus 1 kilohertz or minus 10 kilohertz to plus 10 kilohertz. So, how do you connect this with that? What is the relation? So, this part is not a big deal, but yes, that confusion, eliminating that confusion, making it clear to them, I think is very essential and very valuable. So, this is about all I can think of saying about different parts of this course. The circuits part, which I think is probably not still the pattern followed in other universities, at least they have a separate circuit course I am sure, and signal systems is taught separately. Since we teach both of them here, I did not know whether to leave the circuits out or not, so I mentioned that as well. So, I have said whatever I wanted to say, tidbits here and there from my experience. Now, I think we should really have a few questions, because my time is nearly up. So, if anybody has anything to ask, please.
Sir, signal system is mostly mathematical things. So, means the transfer domain, that is very difficult to make understandable to students, because it's means how the formula derived from the from basics. So, means how we taught in the better transfer domain, because I feel that it's.
You mean they do not get a physical intuition of the transform domain? Is that the problem?
Yes, sir. How we get the physical intuition to students?
Oh, that one easy way to do that is to look at to tell them from the viewpoint of filters. You can say that I can make a filter which selects only one frequency, and so if I apply a sinusoid of the wrong frequency to that filter will allow nothing to pass through, and if I apply a sinusoid of the right filter of the right frequency to pass through, it will allow it to pass through. A still higher frequency, again the filter will not allow to pass through. So, yes, patterns in the time domain become points in the frequency domain, right. So, this I would think one nice way of doing it, because I work in image processing, is to show pictures to people. In short, directly show that the notion of spectrum and properties of the spectrum are better understood in the two dimensional Fourier transform, where we have pictures. We can show that you have a corrugated roof, this tin sheet roof you have, that kind of a pattern. If you submit it as an image and take it from, then you will see clearly that there is an impulse in the frequency domain in one direction at two places. I mean, there are a pair of impulses which show that it is like a cosine, and in the other direction where it is constant, you will just find a DC impulse. So, these things one tries to be as pictorial as possible, and being pictorial tends to help in my opinion. But giving them a feel, getting them to get a feel of it is very, very important. I completely agree there. Yes?
Sir, does that proof include first hand rule?
What is the first hand rule?
Limit h tends to 0, f of x plus h minus f of x by.
Oh no, you don't really have to go. No. You see, you don't have to go through that kind of a proof. What I mean to say is, show that there exist sequences of functions which finally end up in the impulse, and show that each of those, I mean, we have already spent time here telling them what is a function, remember. So, they know what is a function.
No, sir, I am talking about differentiator having memory.
Oh, differentiator having memory, this one. What was the question? The question was whether differentiator has memory or not, right? Okay. Now, if a system has no memory, then the value of the output at some t naught depends only on the value of the input at t naught. Agreed? Right? I am going to use that now. Let us say I want, this is my t naught. At t naught, this is my function. Okay, let us see if I have something in color over here. No, this is a black and white course. नहीं जाने दीजिए, नीचे में कुछ भी नहीं है. Oh, there is something. Yeah, you have explored this system very thoroughly. Okay. So, let us say, look at this proof, it is so simple. Let us say for this input signal, which I will call x1, this was the output signal. So, what do we say? If this signal has this input value, the input signal, then the output has this output value, and this is y1 of t, right. Now, remember, I have to keep reminding you of your own definition. The output at a point depends only on the input value at that point. Okay. Now, I am going to make another signal which goes like this. This is what I call x2, fine. Clearly, the value of x2 of t naught is exactly equal to x1 at t naught, right. So, by our definition, the value of y t at this point, and remember the value of y t is the derivative. This guy's derivative is like slightly negative, this one's derivative is highly, well, I could have made it slightly better, you know, that definitely the slopes are different, right. So, in fact, this curve should not have been like this, it should have been something like maybe something like this maybe. So, it is slightly negative, fine. This is the first one. Now, obviously, the second one will be something like it is more negative than, so this is y2 of t. I am not trying to be accurate, I am just trying to make a demonstration. Now, you tell me if this system is memoryless, how come y2 of t naught is different from y1 of t naught? After all, x2 of t naught is the same as x1 of t naught. If the inputs are the same at any instant, then the system being memoryless should never know that the outputs, I mean should never allow the outputs to be different at the same instant of time, but this one is here and this one is here, which means to say that it is treating this signal, the differentiator treats this signal very differently from this signal, even though at that point their values are the same, that is the critical issue. So, even though the values are same at that point, the outputs are completely different, which means it certainly has memory, it can feel things, it remembers. Am I done? Any questions?